Alright, so just to recap what we've done in trigonometry so far, you spent the last lesson looking at a whole lot of new definitions because trigonometry now is a little bit different from what you were used to seeing back in grade 10. In grade 10 you're using sine law and cosine law and SOHCAHTOA to solve a bunch of triangles, and here we talked about angles being defined on the Cartesian plane. And you saw a whole bunch of different definitions, between principal angles, related acute angles, coterminal angles, and all that kind of stuff. So just a few things to recall. Now we're going to be looking at angles again in the Cartesian plane, so we do have the four quadrants. And just to remember what these different definitions mean, if we're talking about a principal angle, we're talking about an angle that is between 0 and 360 degrees. Okay, so that would have to be a restriction of having a principal angle. And the related acute angle is what we call the angle that the terminal arm makes with the nearest x-axis. So for example, if we were in quadrant 2, this could be our terminal arm, this could be our theta right here. Okay, so the alpha, the related acute angle, would be the angle this terminal arm here makes with the nearest x-axis. So the nearest x-axis is over here, so this would be our alpha right here. Okay, in each quadrant, the relationship between theta and alpha is going to be different based on how the angles stack up. So here, for example, if you're looking at theta, it would be 180 degrees minus alpha. If you're looking quadrant 3 with a different angle, here this would be your theta. Okay, and you have a related acute angle again here with the nearest x-axis. So if you did 180 degrees plus alpha, you then get theta. So again, if you know these relationships, you can easily solve that alpha if you need it. Okay, so take a second here. There's a bit of fill in the blanks here. Try to remember some of the key terms you looked at in the last lesson. So take a minute here, try and see if you fill in the blanks correctly, and then we'll take it up together. Okay, so you can check your answers here. So again, it is the principal angle that always measures between 0 and 360 degrees, okay, because it's rotating in a positive direction and it's less than one rotation. If the angles share the same terminal arm, they are considered coterminal. These are the ones that we looked at where they're just off by different cycles, right? So you can generate a coterminal angle by adding or subtracting a whole cycle of 360 degrees. And you can keep going on forever and find unlimited coterminal angles if you really wanted to. So the related acute angle will be the angle, again, that the terminal arm makes with the nearest x-axis. And because it's an acute angle, it'll always measure between 0 and 90 degrees. So the one that you may have had trouble placing, and you might have only placed it because it was the last one left, was talking about related angles. So related angles produce trig ratios of equal magnitude. And we're going to examine that coming up in a couple slides. Okay. And last but not least, angles that rotate counterclockwise from the initial arm are considered positive. They rotate clockwise is considered negative. Okay, so a couple things to also remember. If you remember our parent functions from the start of the year, we graphed y equals sine x, y equals cos x, and y equals tan x. Okay, so this will be important coming up later when we're trying to prove something, so have an idea of these graphs in mind. So you'll notice that sine x and cos x look very, very similar. They're just off by a little bit by a horizontal shift, which we'll look a lot more at next unit. And tan x here, what's not drawn on here, is the vertical asymptotes that occur. So here we have vertical asymptotes at 90 degrees, again at 270, and again this is a repeating pattern, so this would continue on forever. Okay, so let's take a look at these related angles here. Now, we saw this definition briefly at the end of the last lesson, and when I said related angles all share the same related acute angle. So what that means here, if you look at here in quadrant 1, our angle is 43 degrees. Okay, so there we are in quadrant 1, and our angle here is 43 degrees. Okay, and that's an acute angle, and that's in quadrant 1. In each other quadrant, there will exist another angle that will give us the same related acute angle. So the angle that this terminal arm makes with this x-axis will be 43 degrees. Okay, and there'll be one of these in each quadrant. So let's go and find them one by one. So for the one in quadrant 2, here we'll be going, we're trying to find this angle right here. Okay, so if we want to find alpha, if we have alpha as being 43, if we want to find theta, we know that theta plus alpha will be 180 degrees. So this is for quadrant 2. Theta plus alpha is 180 degrees, and we know that our alpha is going to be 43. Okay, so we can take the time and solve for alpha, and we should find, not for alpha, for theta, and it should give us 137 degrees. Okay, and you can repeat this for any other quadrant you want. So in quadrant 3, let's do the exact same thing. So in quadrant 3, we'll have this related acute angle of 43 degrees. And we want to figure out what the angle is. So here, it's 180 degrees to get all the way to the negative x-axis over here, another 43 degrees to get to your full angle. So for quadrant 3, we're going to say that 180 degrees plus 43 will equal my theta. So that will give me an angle of 223 degrees. Okay, and last but not least, just to confirm that we're on the right track here, I can do this in quadrant 4 as well. So I'll just draw my Cartesian plane. Okay, my arm is going to be in quadrant 4. That will be my theta. Alpha 43. So again, the relationship here will be that theta, so my angle here, plus the 43 degree alpha. Those together will give me a full rotation of 360 degrees. So I can subtract 43 from both sides of the equation and solve for theta. It's going to be 317. It always helps to draw these out. I know it might seem kind of tedious to always be drawing out these angles on Cartesian planes, but having the visual can really, really help see what these are, see the relationships, and make you not make a mistake when you're trying to solve for these. Okay, so with that in mind, now that I have all these related angles, and again, we call them related because they all have the same alpha, I would like you to now, using your calculator, find the trig ratios for each of these. So, for example, on your calculator, if you put in sine of 43 degrees, you'll get 0.682. If you put cosine of 43 degrees in your calculator, you'll get 0.731. If you do tan of 43 degrees in your calculator, you'll get 0.933. Okay, so take a minute here. Finish doing this for the other angles, the other related angles, 137, 223, and 317, and look for any patterns that you might see, and see what the conclusions you might be able to come up with. Okay, so filling in the chart, you might see a bit of a pattern here. You'll notice that the actual value, again, ignoring positive or negative, the actual value is the same for the sine, cos, and tan ratio for each of these angles. Where they differ depends on, I mean, they might be positive or negative depending on what quadrant that they're in. But what we were talking about back in the fill in the blank section way over here, what I talked about briefly, is that related angles will produce trig ratios of equal magnitude. We've just found all the trig ratios for these 4 related angles, and again, shown that all the angles, all the ratios have the same magnitude, whether they being off by positive or negative. So they may differ by the sign, but other than that, the magnitude is going to be the same. So I guess the question is, why do you think this happens? Okay, it's nice that it does happen. It helps us find those ratios sometimes, but why does it happen? Okay, well, let's find out why it happens. Okay, so what I'm going to do here, there's a Cartesian plane, and I'm just going to draw an angle in standard position again. So it starts from the positive x-axis, it's centered, at the origin, and it's going to end at some arbitrary point xy. Okay, so if it ends at xy, I'm just going to draw in my triangle right here. So here I'm creating a little triangle here. I've got a distance of x on the x-axis here, distance of y along the y-axis here. So again, this is just a general point xy. And what I'm going to do is try and write in these ratios, sine, cosine, and tan, for the angle that we have here. So looking at this, sine theta will be equal to y over r. Okay, so I didn't have the r drawn in here. Okay, but again, I have a circle right here, and this radius right here that takes me from the center out to the edge of the circle here will be my distance. So I have 3 sides of this triangle, x, y, and r, and sine of theta will be opposite over hypotenuse, so y over r. Okay, and I can do this for all the other ratios. So cosine of theta will be adjacent over hypotenuse, or x over r. Okay, and tan theta will be y over x, or opposite over adjacent. Okay, and I could extend this to reciprocal ratios as well if I really wanted to. So cosecant will be the reciprocal of sine, so it'll be r over y. Secant will be r over x, and cotan will be x over y. Okay, so, alright, good start. Doesn't really seem like we've done that much right now because I make a general triangle. But let's take this a little bit further. So if we want to look at what relationship exists between x, y, and r, well, I do have a right triangle in here, remember, right? So x, y, and r should be related to each other by the Pythagorean theorem. So x squared plus y squared should be equal to r squared. Okay, so again, all this is well and good, but now how does that answer the previous question? How do we know that the ratios are going to be positive or negative? and in which quadrants they're going to be positive or negative. So let's take a look down here. There's different kind of situations you might run into. So in quadrant 1, for example, if you look here, the x value will be positive, the y value will be positive. Okay, because again, any coordinate you choose out here have both a positive x and a positive y value. So if they're both positive here, looking at our ratios for sine, cos, and tan, if x and y are all positive, and if you can think about how the radius can't be negative, that's always positive because that comes from Pythagorean theorem. If everything's going to be positive here, everything in quadrant 1 is going to be positive. So here, all three ratios will be positive, and that actually is the case. If you look at the table that we came up with over here, everything in quadrant 1, all the ratios were positive. Okay, now in quadrant 2, it looks like sine is positive and cosine and tan are negative, so let's take a look at y. Okay, so again, the first one, all three ratios are positive. In the second quadrant over here, if you're to take a point over in this quadrant, so let's just say I had some kind of point over here. Okay, any x value I have over here is going to be a negative value because it's left of the x-axis. The y value is positive. So in this quadrant, the x value is negative, the y value is positive. So looking at our ratios here, which ones will that affect? So sine is y over r, y is positive, r is always positive, so sine is positive. And cosine, x, which is negative, r, we have x which is negative, r which is positive, so you have a negative and a positive. Overall, cosine will be negative. Okay, and if you look at tan, y is positive, x is negative, so tan is negative as well. So the only one that's positive in this quadrant, quadrant 2, will be sine. Okay, and we can continue this into all the other quadrants as well. So looking at quadrant 3, if you have a point down in quadrant 3, its x value and its y value are both negative. So remember, if you assume that r is always positive, which it has to be, this would make cosine negative, sine negative. With tan, both the y and x are negative, the negatives cancel, you get a positive left over, so tan is positive, everything else is negative. Okay, and last but not least, in quadrant 4, where you have an x value that's positive, a y value that's negative because it's below the x-axis, the only negative one here will be, the negative ones will be sine and tan, the only positive ones will be cosine. Okay, you might be thinking to yourself, how am I ever going to remember which quadrants sine, cosine, and tan are positive in? Well, there's a little bit of a pattern you might be able to use. So if you look at the first letters here, A-S-T-C or C-A-S-T, what might help you remember is to call this the cast roll. Okay, so if you start in the bottom right and go counterclockwise from there, C-A-S-T, cast. C stands for cosine being positive. A stands for all being positive. S stands for sine being positive. And T stands for tangent being positive. So remember this, it'll help you remember which quadrants your ratios are positive or negative in. Okay, and this, again, should follow what you had in the chart back here. So in quadrant 2, you saw sine was positive, cosine and tan were negative. In quadrant 3, tan was positive, the other two were negative. And in quadrant 4, cosine was positive, the other two were negative. Okay, so all that just to come up with a rule that says which quadrants the ratios will be positive or negative in. But the quick way to remember that is just call it the cast rule. Okay, so, and if you want to think about how this works for the reciprocal ratios, whether you want to or not, cosecant, secant, and cotan are the reciprocals of sine, cosine, and tan. So they will have the exact same sign as the ones they're related to. So if sine is negative in a quadrant, that means cosecant will be negative in a quadrant. If it's positive, it means cosecant will be positive. So the reciprocal ratios have the same signs as the original ones. Okay, and if you want to take a look at the graphs here, so what I've done here is I've taken the graph for sine, cosine, and tangent, put them all together, and split up into the four quadrants. So from 0 to 90, 90 to 180, 180 to 270, 270 to 360. So in quadrant 1 here, for any angle between 0 and 90, you'll see that all the graphs are above the x-axis, so they're all positive. In quadrant 2, the sine graph is above the x-axis, the other two are below, so sine is positive. In the third quadrant, tan is positive, the other two are negative, and the fourth quadrant, the cosine graph is above the x-axis, the other two are not. So, a nice little visual representation of why the cast rule is what it is. Okay, so that was a lot of theory. We haven't actually really done much in the way of examples yet. We'll do that in part 2, and we'll see you over there.